So why can a clock on the floor tick more slowly than an identical clock on a shelf, even when nothing's moving? In one lab, two optical atomic clocks separated by just 33 centimeters measurably drifted apart. If we ignored the same effect, GPS would miss your location by kilometers each day. A clock is just a repeatable physical process, and an atomic clock counts an atom's extremely stable rhythm with lasers. When two identical clocks disagree, modern physics treats it as real, not a malfunction. Each clock measures the elapsed time along its own history. That dependence of tick rate on circumstances is time dilation, and it is an observed feature of nature. The puzzle is why gravity alone, with no motion at all, can make the lower clock fall behind. Gravity doesn't just accelerate objects, it creates a tilt in how time flows from place to place. Einstein's clue was the equivalence principle. Inside a closed elevator, constant acceleration and a uniform gravitational field produce the same local effects. Picture a long rocket in deep space accelerating upward, with a clock at the tail and a clock at the nose. The tail sends one light pulse per second. While the pulse is in flight, the nose speeds up, so it meets the next pulse a little later, like a Doppler shift, the change in received pulse rate caused by relative motion. The nose concludes the tail clock runs slow, which is the same as saying the nose clock runs fast relative to the tail. If acceleration can create a clock rate difference between nose and tail, gravity should create a clock rate difference between floor and shelf. How can two separated clocks compare their tick rates without ever touching? They can exchange light because light has a frequency. A count of wave crests arrive in each second. In the 1960s Pound-Rebka experiment, gamma rays sent up a tower arrived slightly redshifted, lower in frequency, matching general relativity, which describes gravity as a curvature in spacetime, the combined arena of space and time. In the accelerating rocket picture, the same shift appears as a Doppler effect caused by the nose gaining speed, so the equivalence principle links the two situations. Now, the key trap: for light, lower frequency also means lower energy, so the top cannot receive the same energy per tick unless its ticks are defined differently. The consistent resolution is that the top clock's seconds are slightly shorter. Higher clocks tick faster, lower clocks tick slower, and the shelf begins to make sense. GPS is a navigation system made of orbiting atomic clocks, and it quietly proves this effect every day. Each satellite broadcasts the time shown on its onboard clock, and your receiver solves for position by comparing signal travel times. Up at about 20,000 kilometers altitude, the satellite sits in weaker gravity, so general relativity predicts its clock runs faster than a ground clock by about 45 microseconds per day. But the satellite is also moving fast in orbit, and special relativity, the tested rule that motion slows clocks, pushes the other way by about 7 microseconds per day. The net gain is about 38 microseconds per day, and since light travels hundreds of meters in a microsecond, that would turn into multi-kilometer navigation errors if left uncorrected. The floor versus shelf difference is the same rule on a much smaller height scale. Can you exploit a higher clock rate to actually gain lifetime? In relativity, the elapsed time on a clock depends on its whole path through space-time, so there's no single amount of time that everyone must share. On Earth, the gravitational part is tiny. Living on a mountain 2 kilometers above sea level for 80 years would amount to only about half a millisecond of extra aging compared to living on the beach. Motion can counteract it, which is why flying in an airplane mixes two effects. Altitude makes the plane's clock tick faster, while speed makes it tick slower. In 1971, the Haffel-Keating experiment flew atomic clocks around the world and brought them back. The clocks disagreed by tens of nanoseconds in exactly the pattern predicted by combining motion and gravity. Time dilation even shows up in particle physics. Fast muons created in the upper atmosphere live longer, as measured by clocks on Earth, and reach ground detectors. The floor clock's disadvantage is the same idea, applied to being lower in Earth's gravity. The answer is that Earth's gravity creates a real gradient in proper time, the time shown by a clock that rides along with you. In general relativity, gravity is curved space-time. Mass and energy change the geometry of space and time. Near Earth, the curvature is slight, but a clock closer to Earth's center sits in stronger gravity and accumulates a little less time per day than one higher up. Pendulums, quartz crystals, and atoms share the same shift because the shift is in space-time itself. That is why the floor clock loses to the shelf clock, why your head is older than your feet, and why GPS must pre-correct satellite clocks. Optical clock comparisons already read out height differences, and researchers are pushing this toward maps of Earth's gravity. Like, if this was interesting, hit the subscribe for more, and turn that notification bell on,